During this segment, we will solve nonlinear inequalities in one variable. For example, we'll solve an inequality such as this. This is a quadratic inequality. If I multiply these two binomials, I would have a quadratic inequality. So be careful and make sure you realize what you're dealing with here. Not a linear, but a quadratic inequality. Here's how we'll solve a quadratic inequality such as this one. First, we'll look at the related equation. In this case, it is x minus 3 times x plus 4 equals 0. And let's solve the related equation. To solve this equation, notice I have 0 on one side. I have a factored polynomial on the other side, so I can use the zero factor property, set each factor equal to 0, and I would have solutions of 3 and -4. Now, these are solutions of the related equation, not the inequality. What we'll do, though, is the following. Take a number line, and on this number line, place the solutions to the related equation only. In other words, don't put 0 here because sometimes it tends to be a little confusing. We'll place only these solutions in the order that they would naturally appear on a number line. So 3, and to the left somewhere, -4. Now notice, these two numbers divide the number line into 1, 2, 3 regions. And here's what's so interesting about these 3 regions. If a single number in, say, this region makes this inequality true, every single number in that region makes the inequality true and is a solution. Same thing with this region and the same thing with this region. And that's what's so nice about the related equation. Solutions divide the number line into regions that entirely are solution regions or entirely are not solution regions. So, how do we find out what regions are solution regions? Well, we just need a test point. Pick any point less than -4 that would lie in that first region. Say -6. Let's check -6. Either -6 makes that a true statement or a false statement. Let's see. -6 minus 3, that's -9. -6 plus 4, that's -2. Is this true or false? Well, this is 18 less than or equal to 0. True or false? That is a false statement. So I would suggest you put some type of X there, telling yourself that that is not a solution region. Now, check any number in this region, any number between -4 and 3. I'll check 0. And I check it in the inequality because we're trying to solve this inequality. Well, if x is 0, what is 0 minus 3? That's -3. What is 0 plus 4? That's 4. Is that a true statement? That's -12 less than or equal to 0. That is a true statement, so I will place a check mark. And I know my check marks are left-handed check marks. You can place a right-handed check mark there. And now check that last region, any number greater than 3. If you want, you can check 100, you can check 1,000. It's up to you, but any number greater than 3. I'll check, say, 4. 4 minus 3 is 1. 4 plus 4 is 8. True or false? Well, 1 times 8 is 8, less than or equal to 0. That is a false statement, so I'll place an X there. And now what we do is the following. We just simply write down those regions that are solution regions, the ones we checked. The only region I checked was this one, so I will write down in interval notation then the solution region. I start at -4 all the way to 3. Now, because this is less than or equal to, or if it were greater than or equal to, I place a bracket about those endpoints showing that this makes it a true statement and this makes it a true statement. And that is my solution for this quadratic inequality. Let's look at some steps we can use. Solving a polynomial inequality. Step 1, write the inequality in standard form and then solve the related equation. Step 2, separate the number line into regions with the solutions from step 1. Step 3, for each region, choose a test point and determine whether its value satisfies the, and this is very important, original inequality. And then step 4, the solution set includes the regions whose test point value is a solution. If the inequality symbol is less than or equal to or greater than or equal to, the values from step 1 are solutions. If less than or greater than, they are not. We'll review those steps as we continue to solve polynomial inequalities. Now notice, this is an inequality and it just happens to be a quadratic inequality. So let's solve using the steps. First, we write down the related equation. The related equation is x squared equals x, and let's solve that related equation. Now, that is a quadratic equation, so let's write it in standard form, x squared minus x equals 0. And then what do? I want 0 on one side and a factored polynomial on the other side, so I will factor out an x, and I'll have x minus 1 is equal to 0. And then remember, we set each factor equal to 0. If you do so, x is 0. That is a solution. X minus 1 is 0, so x is 1. So I have two solutions which I place on the number line, 0 and 1. And now I just happen to have three regions again with which we check. So we now get rid of that related equation and we work on the inequality. Pick any number less than 0. Let's check, say, -1. What is -1 squared? And is it greater than -1? -1 squared, that's 1. Is that greater than -1? The answer is yes. So this is a solution region. Now, pick any number between 0 and 1. It's up to you. If you like to use decimals, use decimals. If you want to use fractions, use fractions. I'll just check, say, 1/2. Is 1/2 squared greater than 1/2? Well, 1/2 squared, that's 1/4. Is 1/4 greater than 1/2? The answer is no, so this is not a solution region. And then choose anything greater than 1. Choose 10 if you'd like. Makes no difference. 10 squared, is that greater than 10? Well, is 100 greater than 10? The answer is yes. This is a solution region. Now let's write down answers by writing down in interval notation the solution regions. You write down from left to right. Now this is greater than. If it's strictly greater than or strictly less than, all things get parentheses. So let's go from left to right. I have from negative infinity, and when I say all things, I mean all endpoints of the intervals, and then I go all the way to 0, parenthesis, and then this is not a solution, so union. Then I start back again at 1 to infinity. If you'd like, check. Pick any number in this region or any number in this region. It will make this a true statement. So here is the solution set written in interval notation of this quadratic inequality. Checking, say, -6. And it helps to at least look at the number itself. I'm going to let you check this one, but I'm going to check something like, I'm going to check 0, and I'm going to show you a little something that will help you out. Let's check 0. Obviously, it's this region, and obviously, it's a simple number to check. But if I check 0, if x is 0, that term is 0. If x is 0, that term is 0. And I have 25 greater than or equal to 0. True or false statement? Well, that is a true statement, so this is a solution region. Now, you should check a few regions, but I know the following. As long as no factor occurred more than once, for example, each of the 4 factors I had were unique factors, then the regions that work and the regions that don't work will actually alternate. So I know this region works, which means this one won't, and this one will. It means this region will not work, and this region will. But you should check a few regions. Don't rely upon just one region. Check a few just as a checking standpoint. Now, let's write down our solutions. And as a matter of fact, make sure you check another region here, but we're okay since we're working it together. Now let's write down our solution from left to right. Everything except the infinities, every endpoint of my intervals gets a bracket because of this inequality symbol. So from left to right, negative infinity to -5 bracket, union. Here I have -1 to 1. -1 to 1, union 5 to infinity. And there we go. Here are the solutions, or this is the solution of this polynomial inequality. Again, double check, make sure your intervals are okay. But that's a good little checking point also. Now let's see how we can solve a different type of nonlinear inequality. What about solving a rational inequality? Step 1, solve for values that make all denominators 0. Step 2, solve the related equation. Step 3, separate the number line into regions with the solutions from steps 1 and 2. Step 4, for each region, choose a test point and determine whether its value satisfies the original inequality. And then step 5, the solution set includes the regions whose test point value is a solution. Check whether to include values from step 2. Be sure not to include values that make any denominator 0. So notice this is an inequality and it's a rational inequality. One of the most important things is to be able to identify rational inequalities. Now that we've identified this as a rational inequality, let's solve this inequality. Remember our first step? To include on this number line any numbers that make the denominator 0. Notice by inspection, 4 makes this denominator 0. Since it does, I will include 4 on my number line. Now we'll look at the related equation and whether before we were looking at this equation or the inequality, 4 is still a value that makes the denominator 0. Let's now, though, move on to the next step, which is to solve this equation. So how do we solve this equation? Well, we look at this equation, we notice it's an equation with rational expressions. The LCD is x minus 4, and we multiply both sides by the LCD. So the left side by x minus 4, and the right side by x minus 4. Notice on the left side, the x minus 4's divide out, and I have x plus 1. The right side, 0 times x minus 4, is simply 0. And then solving, we'll have x is negative 1, another number on the number line. And now, just as for polynomial inequalities, now we check these regions in the original inequality. Now, by the way, I know I have 4 on this number line, but it doesn't mean I'm going to include 4 in my solution set. Can you agree that x cannot be 4? So it's not going to be a solution, but we still need it on the number line. Check any number less than negative 1, check negative 100 if you want. Let's check, say, negative 2, and I'll have negative 2 plus 1 over negative 2 minus 4. We just want to know, does any number in this region make this a true or false statement? Negative 2 plus 1, that's negative 1, and in the denominator, that's negative 6. So is that a true or false statement? Well, negative 1 over negative 6 is 1/6. 1/6 is greater than or equal to 0. So this region is in the solution set. It is a solution region. Check any number between negative 1 and 4. I will check, I'll check 0. So 0 plus 1 over 0 minus 4, true or false statement. That's 1 over negative 4, true or false. Negative 1/4 is not greater than or equal to 0, so this is a false statement, which means that's not a solution region. And then I'll let you check something greater than 4, check any number greater than 4, you'll find that it is a solution region. By the way, if you're wondering, you might want to experiment a little bit around too and see if these don't alternate again as what we were talking about with polynomial inequalities. Just be careful when you have any kind of a factor occurring more than once. Now, let's write down the solution set in interval notation. Normally, with greater than or equal to or less than or equal to, all the endpoints of the intervals get brackets, except this can never get a bracket. We cannot include 4 in our solution set. So let's write things down from left to right. Negative infinity to negative 1. I will include negative 1. It did not come from the denominator. Union 4. I will not include 4, so I'll put a parenthesis and then to infinity. And you can check a few numbers in each region. These numbers will all make this a true statement. At this time, practice solving all types of nonlinear inequalities. Just remember, if your inequality is less than or greater than, all of your numbers get parentheses, less than or equal to, greater than or equal to, everything gets a bracket. All of your endpoints of your intervals get brackets, except any numbers that came from the denominator of rational inequalities.